So an example of the Legendre transform is the Lagrangian and the Hamiltonian, functions of Lagrange and Hamilton. And now the Lagrangian is a function of Q and Q dot and sometimes of the time. If it's only a function of Q and Q dot, then dl is this. P is always the partial of the Lagrangian with respect to Q dot. You define the Hamiltonian like this. dH then is P dq dot plus Q dot dP minus dl, and then when you add in what dl is, minus partial L, partial Q dq, and so forth, this term cancels that term, and what you have left is Q dot dP plus partial L, partial Q dq. And that says that the Hamiltonian is a function of P and Q. And an example of that, well, at that stage, though, you want to re-express Q dot in terms of P and Q, and you have to use this equation to do that. When the Lagrangian is quadratic in Q dot, then that's very easy because P is just mQ dot, so Q dot is just P over M, and the Hamiltonian takes the form that you've seen many times, namely for a harmonic oscillator, P squared over 2M plus M omega squared Q squared over 2. You can also go the opposite way. Good God, this is really quite awful. All right, so I'm gonna have to use the boards, and oh wait, now it's come up again. Jesus. All right, so you can also go backwards, and you can define Q dot as partial H partial P, and set L equal to PQ dot minus H, and then you find that DL is P to Q dot minus partial H partial Q to Q. So that says that L is a function of Q and Q dot. So you can go in both directions. And thermodynamics makes all right, we've got to do something about this. This is really stupid. Well, thermodynamics provides many illustrations of the change of variables. Oh, let's see, the grader is out there with some homework. Are you going to, why don't you just put it in the students' boxes?
Okay, where are the boxes?
I don't know, around the corner maybe?
Okay.
Of course, you may not be able to get to around the corner from there. Anyway. So, the internal energy, for example, is, we saw in equation 111, that the du was TdS minus PdV plus the sum of chemical potentials times the change in the numbers of the molecules. And so then you can change the independent variables from S, this U is a function of S, V, and the N's. If you change from those to SP and N, you can do that by adding PV to the internal energy. Then you get something called the enthalpy. And if you form its differential, you see that it's properly a function of entropy, pressure, and the numbers of particles. On the other hand, if you subtract the temperature times the entropy from the enthalpy, you get what's called the Gibbs free energy. And that turns out to be, that's H minus Ts, and dG then is VdP minus SdT, and then numbers of particles. So the Gibbs free energy is a function of pressure, temperature, and numbers of particles. One of the advantages of that is that the pressure and the temperature and the numbers of particles are things that are immediately accessible to somebody doing an experiment, whereas the enthalpy is a function of the entropy. Well, who knows what the entropy is of the sample that you're dealing with? And over here, once again, the internal energy is a function of the entropy. And so it's not obvious what that is. So one of Gibbs's many contributions was to invent a free energy that you could, that experimenters could compute, because they could measure the pressure, the temperature, and the numbers of particles. The Helmholtz free energy is the internal energy minus Ts, and that's a function of volume, temperature, and numbers of particles. So that also is one that is accessible to measurement. That's also a useful free energy. Now, the principle of stationary action in mechanics, maybe I'll, since this isn't an example, but is part of the actual text without an example. This is the action, not the entropy. We're talking, it's a time integral of something called the Legrangian, and the Legrangian is a function of q dot t, and it's a time integral of that. Now, in here, I'm thinking of Q as Q1, Q2, dot, 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 up to Q3n if there are n, capital N particles. And the change in the entropy then is, I'm sorry, the change in the action, not the entropy, is then a sum, I equals 1 to 3n, integral T1 to T2, and then it's partial of a Lagrangian with respect to Qi, change in Qi, plus partial Lagrangian with respect to Qi dot, times the change in Qi dot, and it's all of that integrated dt. The change in Qi dot is Qi dot plus delta Qi dot minus Qi dot. And so it is just the time derivative of the change in Qi. That's something that can be confusing, but here, let me throw up the right equations on the board, so you'll have two descriptions of everything, or two images to look at. So the change in the action then is an integral and a sum over I, and it is partial L, partial Qi, change in Qi, plus partial L, partial Qi dot, time derivative of the change in Qi, and all of that integrated dt. And so then you could integrate by parts this term here, and if you do, you then get partial L partial Qi minus d by dt partial L partial Qi dot times the change in Qi and all that integrated dt, plus a surface term. And the surface term is sum on I partial L partial Qi dot change in Qi evaluated at T2 minus the same thing at T1. So the principle of stationary action is that the action should be extremal, that is to say maximal or minimal on the for classical processes, or for processes that obey the classical equations of motion. And so what we mean here is that of all the ways in which you can go from T1 to T2, and from a 1Q, let us call it Q1 to Q2, both of them being 3n vectors. So we keep T1 and Q1 fixed, we keep T2 and Q2 fixed. The endpoints are fixed, and we're just varying the paths. And we're only varying the paths infinitesimally. And so the point is that the true path is one such that when you do vary it slightly, the change in the action to first order to lowest order in the change in Q is 0. Notice that if we're trying to do this exactly, the change in the action would not just be linear in delta in the change in Q. It would involve quadratic terms and cubic terms and cross terms of all kinds. But we're just considering the limit in which the change in Q in all the Q's is infinitesimal, and we don't change the endpoints at all. So that means that the delta Qi at the endpoints vanishes. So this term here we can forget about. And then if we want this to be extremal with respect to any arbitrary change in the path, then this thing has to be identically 0 at all times. And so what we get is Legrange's equations, which are a little bit lower here. We get Legrange's equations, which are d by dt partial L partial Qi dot minus partial L partial Qi has to be 0. So that's this term in parentheses has to be 0 identically. And conventionally, one puts the d by dt part there first. You recall that when we changed variables going to the Hamiltonian, this was actually pi. So this is pi dot is equal to partial L partial Qi, and partial L partial Qi is actually minus partial of the potential energy with respect to Qi. So this is the form that Newton's laws take. This is the way you normally see classical mechanics presented. Now, I've been picking, if I did this for, boy, this is really, I just put the coffee cup down and Anyway, I did this for a general Lagrangian that may depend upon time as well as the 3n q's and the 3n q dots. On the other hand, if it seems to respond when I touch the blackboard, strange. Okay, if L is simply L of q and q dot, no time at all, then we say that the system is autonomous. And in that case, the energy is conserved, and the energy then is a sum on I of pi qi dot minus L, or as we write it, this is the way one normally defines the energy here. And the reason this is conserved is that then E dot is then a sum on I ddt of partial L partial qi dot times qi dot plus partial L partial qi dot qi double dot minus L dot. That is to say, the total time derivative of L. But the total time derivative of L, if L doesn't explicitly depend upon time, and I'm running out of blackboards, so I'm going to write this total. I'm going to rewrite this equation here. It's E dot is equal to a sum on I of ddt of partial L partial qi dot plus partial L partial qi dot qi double dot. And now we subtract the time derivative of L, and so that's minus partial L partial qi times qi dot minus partial L partial qi dot qi double dot. But there's no extra term because because partial L partial t is equal to 0. And so what we see is that this term cancels this one, and this one cancels this one because of Lagrange's equations. In other words, this thing is equal to that thing, and so the whole thing is 0. So we get to E dot as 0. Well, this is something that you've known for a long time. Let me, since this system here is so flaky, I think I'll continue. In fact, I'll have to continue. Pi is said to be the momentum canonically conjugate to the variable qi. And if we can then, oh, I'm sorry, there's an error. If we can invert and solve for qi dot in terms of the pi's and qi's, then we can have a Hamiltonian function of q and p be a sum pi dot qi dot of q and p minus L of q and p. So so here what we're doing is we're imagining we can rewrite, we can solve for the qi dots in terms of the p's and q's, and then we get a Hamiltonian that's just in terms of the p's and q's. the change in the action due to a tiny detour that changes only at the end point. So now let's go back to this equation. The change in the action in general is this plus these end terms. So if we just change the Q at the end points, then we get that the change in S is a sum. These are PI's, and these are change in QI's. And so we get the equation that partial of the action with respect to QI is PI. And we can also compute the total time derivative of the action. And the total time derivative of the action, since the action, again, we're just varying the action, let us say, at time t2. We're varying things at t2 now, whereas previously we kept everything constant at t1 and t2. Now we're varying things at t2. So d by ds is just L at t2. On the other hand, that has got to be partial s partial t plus partial s partial the q's at t2 times qi dot at t2, because let's see, where was the endpoint equation? You see, it's partial L partial qi dot times delta q oh, I'm sorry, I'm taking the time derivative here. So this is the time derivative of the action, and then we can rewrite this as partial s partial t. Partial s partial qi is pi, and that's p, and that is pi. I'm getting pi qi dot. What? Right. That's right. There's actually a typo in the. Okay. So let me just mark that typo on my notes here. So what we find from this then is that the partial of s partial t is then L minus a sum pi qi dot, but that is just minus h. So what this tells us is that the time derivative of the action is minus the Hamiltonian, and the understanding there is that we just let the process continue a little bit in time at t2, and the change then in the action will be minus h of t2, h at t2 times dt. Now, just wondering if I can get this to turn on, because it would be a lot of help to be able to use this. Well, there's no point in. All right, the next topic is symmetries and conserved quantities. This is an important and rather nice topic, and it's one that was invented by a German mathematician named Emmy Noether. And she was born in 1885 and died in 1935. And I think she became a professor at one of the Ivy League women's colleges, in those days the women's colleges and men's colleges were separate institutions. Anyway, what she was looking at was, let's think about, or would we be better off maybe on that board there, because if we go there, I'll be closer. So you, are you closer? Oh, maybe not, I'm wrong. All right, let's just go over here.
If we're not going to use the computer, can you shut it off? Because that's really annoying.
Say it again, what?
Can you like unplug the computer so it stops flashing?
That's a good idea. There we are. All right, so I'll turn power off. Well, I could even use these middle boards, I guess. I didn't really erase them though, because I thought that the electronics would work, but okay. So what Noether considered was, let's change Qi to Qi prime, which is equal to Qi of t plus some small change of Qi of t. And if we do that, then Qi dot prime will be Qi dot plus the time derivative of the change in Qi dot. And the change in the Lagrangian will be, of course, the sum over I, partial L, partial Qi, change in Qi, plus partial L, partial Qi dot, change in Qi dot. And what we're thinking of here is a system that has a symmetry. And what we mean by this, by symmetry in this case of mechanics, what we mean is that the change in the Lagrangian is 0 when we go from Qi of t to Qi prime of t by a small change in Q, the Qi's. And so we're saying that this is actually equal to 0. And what that will imply is that something is conserved. And the conserved quantity, which Noether discovered, is very general, you see, because it's true for basically any system. I'm doing it here for mechanics, but one can also do it for, not simply for quantum mechanics, but quantum field theory, classical field theory. It's very, very general. And to see that Q is a conserved quantity, what we do is we compute its time derivative, and we get that Q dot is the time derivative of that, so that would be sum of d by dt of partial L partial Qi dot times the change in Qi plus partial L partial Qi dot times the time derivative of the change in Qi dot. On the other hand, this thing is the partial of L with respect to Qi, where what we're saying is that this thing is conserved as long as the equations of motion, the classical equations of motion, are obeyed, and consequently Lagrange's equations are true. So this is partial L partial QI. This is the change in QI, and the other one is partial L partial QI dot, change in QI dot. But that's what we assumed was zero because of the symmetry. And so the time derivative of Q actually is zero. There are two famous examples of this. Imagine that the variables are Ri, which is QI1, or if, to use a more familiar language, Ri is Xi, Yi, Zi. We can imagine that the symmetry is that that the change in Xi is A, change in Yi is B, change in Zi is C. So that means that the system is invariant under a translation. In that case, what is Q? Well, Q would be the partial of L with respect to QI dot. Those are the momenta. And now what's the change in the QIs? It's just A, B, C. And so if we let D vector equal A, B, C, then this says that PI dot D summed over I, this is QI dot, Q dot vanishes, but this is just D dotted into the sum of the PIs. And so this is the momentum. And so this says that the momentum in the direction D, total momentum of the system in the direction D is conserved. And since these were arbitrary directions, the whole momentum in any direction is conserved. We could do the same thing for, we can imagine that the system is invariant under rotations. And so here, the change delta Ri is theta cross Ri. That's what a rotation does. That's a rotation about the angle, a rotation of magnitude. The angle here is, the amount of the rotation is the length of the vector theta. The axis of rotation is the vector theta. And this is a right-handed rotation about theta. So the change in the Ri's are that. And then the thing that's conserved is Q is equal to a sum on I of partial L partial VI, that's this term, times the change in Ri, and that is then sum on I partial L partial, well, let me switch immediately to PI. This is PI. And this is theta cross Ri. And you can manipulate this using the Levi-Civita symbol if you want, because this is pi epsilon, I'm sorry, it's not pi, it's pi, let us say, I'm looking for some indices. Let us say J, the jth component of that times the jth component of this, which would be epsilon j, theta, epsilon j, KL, theta j, RI, L. And now this is cyclically, this is invariant under cyclic permutations, and so we can rewrite that as a sum on I of Ri cross Pi dotted into the vector theta, but this is just the total angular momentum dotted into theta. And so this says, and the quantity that's conserved is the angular momentum in the direction of theta. So if the what was the original statement? The original statement was that the Lagrangian is invariant under some change. If the Lagrangian is invariant when you rotate the system about an angle theta, then the angular momentum in the theta direction is conserved. All right. So now, are there any questions, by the way? All right. The next topic is homogeneous first order ordinary differential equations, and I think I can start the discussion on these boards. So what we're going to assume here is we have a differential equation. 0 is p of xy dx plus q of x and y dy. So that's our first order differential equation. But we're going to assume that p and q are homogeneous of degree n. So p of tx ty is t to the n p of x and y, and q of t x ty is t to the n q of x y. And we're also going to make a change of variables. We're going to change y. We're going to let y of x, and of course that's the solution that we're looking for. We're going to let y of x equal x times some v of x. So v of x is just the unknown solution y divided by the independent variable x. And then what we have is dy is equal to v dx plus x dv. And so if we substitute those into this equation, what we get is p of x and v, p of x and xv, because y is xv, dx plus q of x and xv. And now dy is v dx plus x dv, so it's x dv plus v dx. So all that is equal to 0. But now what we see is we have a way of using the homogeneity, because this is equal to x to the n p of 1 comma v dx plus x to the n q of 1 comma v times x dv plus v dx equals 0. And we can then massage this equation, divide by x to the n, and so forth, or even x to the n. I guess just x to the n. And what we get is dx over x plus q of 1v divided by p of 1v plus v q of 1v all of that, this dv is equal to 0. So now we've got an equation that's separable and separated. We can integrate that to log x. We can integrate this to, well, if you've got Mathematica or Maxima or something that will do it for you. This may not be an easy integral, but whatever it is, you can certainly do it numerically. And the solution then is that log x plus whatever that indefinite integral is of q of 1 v prime over p of 1 v prime plus v prime q of 1 v prime dv prime is equal to a constant, because the differential is 0. And so this is an equation that involves v and x, and so you solve for v of x. And then to get y, you write y as xv of x. And so that's basically yeah, I've used up all the boards. All right, so let's go over here and what I'm going to derive now for you is a recipe, because a linear first order ordinary differential equation always has an integrating factor, and so you can always solve it. And so let me get a new piece of chalk and show you how this works. So the equation we're going to start with is dy dx plus r of x y, and putting all the variables, y of x is equal to s of x. And the idea is you can always find an integrating factor that makes this equation exact. And we can rewrite this equation as 0. The integrating factor is going to be alpha, so we're going to multiply this equation by alpha. And then we're going to rewrite it as alpha ry minus s dx plus alpha dy is equal to 0. So that's you just basically multiply the whole equation by dx, and that gives you that. So now what we do is we basically have p equal to alpha ry minus s, and q is equal to alpha. And so the condition that this be exact is a y derivative of p, which is just alpha r, should be the x derivative of q, which is the x derivative of alpha. Well, this is an equation that's pretty easy to solve. It's d alpha dx is equal to r of x times alpha of x. And that's one of those equations that we like to solve because it's just our favorite thing. It's an exponential. So the solution is alpha of x is some alpha of 0 e to the integral 0 to x of r of x prime dx prime. Now I did that one in my head rather than following the notes, and what I'm going to get back to the notes exactly, I'm going to replace x equals 0 by x0 and that by alpha x0. So you can see that this equation, this is a solution of this equation because d by dx just pulls down an r of x. So now we have the integrating factor, and that satisfies the equation alpha r equals the x derivative of alpha. So this original equation is now of the form alpha, the x derivative of y plus alpha r y. So that's this here is, and that's equal to alpha, the x derivative of y, plus the x derivative. Alpha r, of course, is the x derivative of alpha. So this thing is alpha, the x derivative of alpha times y. And that is just alpha y, the x derivative of alpha y. And that is equal to alpha s. And so we write that as alpha s. And now this is an equation that's very much like the first equation, namely that we can just say that alpha of x, y of x, is alpha of x0, y of x0, plus an integral from x0 to x of alpha of x prime, s of x prime, dx prime. So that means we're basically done, because we know what alpha of x is. We now have an equation for y of x. We just have to integrate the source term times alpha of x, which we know, and add it to this, and we get the final answer, which is y of x is equal to alpha of x0, y of x0, divided by alpha of x plus 1 over alpha of x times an integral x0 to x, alpha of x prime, s of x prime, dx prime. And here the function alpha is this exponential given in terms of alpha of x0, and another way of writing that then is that this is equal to e to the minus integral r of x prime dx prime from x0 to x, all that times y of x0 plus an integral x0 to x of an exponential in here, which was x0 to x prime, r of x double prime, r of x double prime, dx double prime, and then s of x prime, dx prime, close parentheses. And what we have here is the general solution of this inhomogeneous first order differential equation is the general solution to the homogeneous equation, which is this term, plus a particular solution of the inhomogeneous equation. And that's the general form of such solutions to inhomogeneous equations. It's always general homogeneous plus any old solution of the inhomogeneous equation. So let me see what the time is. We've got about 20 minutes left. I have various examples of this. Let me just give you the solution of the equation. The Newton's law for a falling body is the mass of the body times the time derivative of the velocity, which is, say, the acceleration, is the gravitational acceleration minus an air resistance term times the velocity. This is the velocity in, I guess I'm doing the velocity going down, so V was directed this way. The solution of this is V of t is equal to mg over b plus the initial velocity minus mg over b times e to the minus bt over m. So this is the equation for falling bodies in viscous media. Well, I guess air is what I'm thinking of, because if we had something like water or some other fluid, then this term would be much more complicated. Some amusing aspects of this is you can see that after the object has been falling for a while, this exponential is 0, and this is the terminal velocity. And for a man falling, the terminal velocity is 200 kilometers per hour. On the other hand, a peregrine falcon diving can reach or exceed 320 kilometers per hour, as can a falling bullet. On the other hand, you can see if the mass is small, then the terminal velocity isn't very big. And that's why insects manage to fly around, because the ratio of m over b is fairly small. So they don't fall, their terminal velocity is quite low. And that's why mosquitoes are a problem, basically. In particular, mice can pull down mine shafts and run off unhurt, and of course insects and birds can fly. Okay, I'm going to skip the other examples and go on to small oscillations, which is also of some real physical interest. So I guess I'll go over to this board here. So what I'm talking about here then is that L is a sum I equals 1 to 3 n mi over 2 xi dot squared. So this is the standard. This is mv squared over 2, and then minus the potential energy term, x being a 3n vector. And now you can make some transformations of variables here. You let qi equals square root of mi over m times xi, and you let u of x equal v of q, or v of q equal u of x, and you can then what you've got is you can write this as m over 2 q dot q dot minus v of q. So this is a vector equation, and that's a vector. This is a scalar product of two vectors. So now we've got a rather simple equation, and the Hamiltonian then is 1 over 2m p dot p, where it's made out of the pi's, and plus V of Q. And this is conserved because there's no explicit time dependence in the Lagrangian. So this is time independent, and for nice problems, this V of Q has a minimum. And of course the minimum of the Hamiltonian then is P equals 0, and Q is wherever the minimum of V is. Of course V might not have a minimum, but in nice physical problems, V does have a minimum. And so then what one can do is expand the Lagrangian in this way: m over 2 Ri dot squared summed over I minus a half sum on jk, and it's rj rk times the second derivative of v with respect to qj qk at the minimum. So q0 is minimum of v, and so partial v partial qi at q0 is just 0. And so these r's, we can make yet another change of variables and write this as 1/2 or m over 2 sum si dot squared minus v double prime I si squared, and these si's then are the normal modes of the problems, of the vibrations just occur about the minimum. What happened here is that you see this second partial derivative at the minimum, this thing, first of all, if it's a minimum, then the thing is going like that, and so the second partial derivative is positive. Moreover, it's also symmetric, and it's certainly real. So it's a real symmetric matrix. It can be diagonalized by an orthogonal transformation. So V double prime can be written as O transpose V double prime diagonal O. And so this VDI is the ith element on the diagonal of the diagonalized potential at the minimum. And those are the normal modes. As you know, you can you have MATLAB free at UNM. The result of this is that you can do all sorts of things using MATLAB, and one of the amazing things that you can do is integrate systems of differential equations. And let me just see, what is the time? Okay, we've got about 12 minutes left. Let's look at an autonomous system. System of first order ODEs looks like this. X1 dot is F1 of X1 Xn dot 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 Xn dot is Fn of X1 dot 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 Xn. So that's an autonomous nth order, or a first order n-dimensional, I guess, autonomous system. It's autonomous because the f's don't depend on time. But now, it turns out that this can describe a much more general situation than than it seems. In other words, it's first order here, and these f's don't depend upon time, but by going from an nth order system to an mth order where m is higher, one can describe systems that have higher time derivatives and that also have time, also are time dependent. And the way one does that is, for example, you set t, or you set x n plus 1 equal to t. And so then x n plus 1 dot, well, that's t dot, so that's just equal to 1. And bingo, you're now able to describe a system. In other words, if there were a t here, you just call that xn plus 1. And then you say the time derivative of xn plus 1 is equal to 1. So now you've turned a non-autonomous system of nth order into, you've turned a non-autonomous system of nth order into an autonomous system of n plus first order. You can also, similar tricks, you can turn things into, you can have higher derivatives with respect to time and recast them as first order autonomous systems. The example that I worked out for you was this one. I have two second order nonlinear differential equations. So that's one. This so here are two equations that I would not try to solve by hand, but one can write that as an autonomous fourth order system. X1 dot is, well, let me say what the tricks are. The tricks are that you set x1 equal to x dot. You set x2 equal to y dot. You set x3 equal to x, and you set x4 equal to y. And at that point, this can be rewritten as the autonomous system of fourth order. X1 dot is minus r x3 times x3 squared minus a squared minus g x3 x4 squared. X2 dot is minus r x4 squared minus b squared minus g x4 x3 squared, and then x3 dot is equal to x1, x4 dot equals x2. Well, I had MATLAB solve that thing, and the solution is in the book, and if we had the cable working, you could see it. What's plotted there is 400 time steps. I said R equal to 0.2, A equal 10, B equal 10, G equal 1, and initial conditions, X of 0 equal to 5, Y of 0 equal to 5, X dot of 0 equal to 10, and Y dot at 0 equal to 0. The MATLAB scripts are available to everybody on GitHub, and so you just go to that address and you can find on them. This next section here, I think, well, the first part of it, I guess, is worth looking at. Namely, if you have an equation that looks like this, d by dx of something, p n minus 1, y, let me just call it n minus 1, that's the n minus first derivative, plus p n minus 2, y n minus 2, the n minus second derivative of y with respect to x, plus dot 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 plus p0 y. If that's equal to 0, you can, it turns out that that is exact. And an example is, suppose you have 0 equals d by dx of y prime plus x squared y. Well, that can be rewritten as y prime plus x squared y is equal to some constant. And so now you can integrate that, and what you get is that y of x is e to the minus x cubed over 3 times some other constant plus c times an integral 0 to x e to the x prime cubed over 3 dx prime. So that's an example of this. I think I'm going to skip the constant the constant coefficient, actually the constant coefficient is a cubed thing, and it's related. Remember, if when we had constant coefficient differential equations, or in fact partial differential equations, I said to you, you can always solve them by the Green's function method. If you have just various constants, c, I, j, say, partial I plus j partial x I partial y j acting on g of xy, and we want to write that as delta of xy. You write this as a Fourier transform, and the g would be an integral. Here it would be d to dx dk. Well, it depends on what we call them. We could call them dk dl, and e to the I kx plus I L y, and then you divide by something like Cij k to the I L to the j, and there are various terms of I here. I'm not sure what the terms of I are, and we have a 2 pi squared here. And I'll say I to some power, which I'm not going to figure out for you. N of ij. That's, I guess, general. Well, it turns out that for differential equations, it's sort of amusing if you have a sum ck dky d t to the k equal to 0. Well, you can just let y equal to e to the zt, and then what do we get? 0 is equal to sum ck. The kth derivative of y, of y with respect to t, is going to be z to the k, and what's left over is y, so you can factor out the y, so you get an equation, sorry, that's ck z to the k. So you solve this equation for z. The fundamental theorem of algebra tells you that there are, if this is k equals 0 to n, will be n roots of that by the fundamental theorem of algebra. And so you solve them, find them, and then you get n solutions to those different values of z. So let's see, are we out of time now? We have 1 minute left. Is there a question? Well, I think maybe we'll stop here because the next topic is singular points of differential equations, and that's related to the Frobenius.